I'm Björn Lund. I'm the director of the Swedish National Seismic Network, and we operate the network in Sweden that collects data for earthquake and blast analysis. Sweden has not very many earthquakes, so we record about 2 earthquakes a day, but we do record a lot of blasts from mines, from quarries, and from construction work. So we're quite used to this problem of distinguishing blasts from earthquakes. We're mostly interested in earthquakes, of course, but to do that, we need to get rid of the blasts. And of course, on Monday, it was the other way around, trying to identify what we actually detected in this area south of Sweden.
So tell me how this unfolded. How did you first come to notice these spikes?
The data from our stations are streamed continuously into the center here in Uppsala. And we also get data from our neighboring countries, so from Denmark and from Norway, Finland, and the Baltic countries. And the data is processed automatically. So we have 2 automatic systems that go through the data and look for things that could be earthquakes or blasts. And so generally it only takes a few minutes until we have a first location and estimate of the magnitude of a seismic event. And this also happened on Monday. So the first event occurred at 2 o'clock in the morning Swedish time, and we had an automatic location very quickly southeast of the Danish island of Bornholm. And then later in the afternoon or evening at 7 p.m., there was a second event, this time northeast. It was 5 UTC, and a lot of us, well, all we seismologists use UTC, but okay. So it was 7 in Sweden. So we detected these 2 events. Detecting blasts in the Baltic is not very unusual, and this is something we do on a regular basis, weekly, I would say probably more than weekly. There's a lot of Navy exercises going on in Sweden, in Denmark, in Finland, in the Baltic countries, Germany, Poland. And we also detect spurious events in the central Baltic that we really don't quite know what they are. But so there's nothing strange about these events, or was nothing strange in the beginning. And their magnitude wasn't big enough that this sort of triggered us. It was not until on Tuesday when we realized that the Nord Stream pipes were leaking, that we were actually approached by Swedish TV that wondered if we had detected something in the area. And then we went back to look at these events, and yes, we manually relocated them. We looked at the data closely, and we could then determine, and to my mind very confidently, that these are blasts. And the first one was located to the southeast and about 12 kilometers away from the area where the gas is leaking. Mm-hmm. So that's not very accurate, but we know we have problems with location accuracy of seismic events in this area. So we're not that close, but it's still fairly close. And when we looked at the second event, then we locate that about 6 kilometers away from where the Swedish Maritime administrations say that the gas is leaking out. And we have a location uncertainty in that area, which is about 3, 4, 5 kilometers. And the uncertainty in the location of the gas leak, I have now discussed this with the Maritime Administration, and they agree that they have about 1 kilometer uncertainty in the coordinates that they give out, which means that our location is pretty much in the area of the leak.
You know, I think a lot of people's perception is there was this alert at 2 a.m., people got out of bed, they were really concerned. But actually, your system picks up, as you said, blasts and earthquakes on a regular basis, and that's why you're able to tell the difference between the two.
Yes.
Can you walk us through, for someone like me, or others who may be watching who aren't experts, who don't know how to read the differences? What are there visual differences between a blast and an earthquake? How do you tell? How can you tell?
Yes, so an earthquake and a blast, when you look at what happens at the source, are 2 very different phenomena. An earthquake occurs on a fault in the earth somewhere where one piece of rock moves over the other piece of rock on the fault. So it's sort of what we call a shear movement. And that creates seismic waves that radiate out in all directions with a particular pattern in terms of different types of waves. We get waves that are quicker, and we get waves that are slightly more slow, and we also have waves that only propagate on the surface of the Earth. If we have a blast is basically something that goes from a very small volume to a very large volume. So we have volume expansion in all directions, which is very different than to this slip on a fault. And so the seismic waves that are generated are inherently different. They're different in size and frequency content. So when we compare these two, we can usually pick out that this was an earthquake and this was a blast. It's not always that easy, especially for shallow earthquakes and blasts that occur in a mine or in a quarry, for example. They can be fairly similar. Blasts that occur in a mine or in a quarry can be very similar to a shallow earthquake. But we have another advantage here, and this is that this blast occurred in water. And if you have a blast in the water itself, then you also get waves that sort of bounce from the blast. They bounce to the surface of the water column, they get reflected back down, they bounce off the bottom of the sea and then back up. And this creates a whole set of extra waves, we can say, which are quite indicative of something occurring in the water column. So we have these two different pieces of information. And then additionally, we have also recorded a lot of Navy blasts to the north of this region. So the Swedish Navy has a naval base there. They do regular exercises, and they're often very good about telling us that they will blast, and sometimes they also tell us the amount of explosives that they use. If they have a mine, for example, that you would use for a ship or a submarine, and so they've told us, well, that's 105 kilos of TNT equivalents of explosives in this. And we have a couple of these events, so we can actually compare Monday's events to these blasts, to the magnitudes that they would, that we estimated for these blasts, and then back calculate. Both we can see that what happened on Monday are underwater blasts, and we can also get an estimate perhaps of the amount of explosives that were used in the blasting.
That's fascinating. So do you have that estimate? Have you come up with that estimate yet?
So we estimate that it's probably somewhere, it's more than 100 kilos of explosives, probably not much more than 200, but in that range probably. So this is for the second blast. So we only detect two blasts.
Right.
Even for the northerly section of the pipeline, there are two leaks, but we cannot really see that. We're looking into that at the moment to see if there could have been two almost simultaneous blasts.
Okay.
But that's not something that we can see very clearly in the data, at least not right now. So we're continuing to look into that, but it looks like one blast. How that created two leaks in the pipeline, that is of course a very good question, but we can't really say anything more at this moment than it looks like one blast.
So if you could recap that for me, the amount of explosives that you have calculated for the two separate events are about between 100 and 200, you said?
Yeah. So for the larger event in the evening, on Monday evening, we estimate to somewhere between 100 and 200, or maybe a little bit more, that sort of range of amount of explosives. The first event on Monday morning was smaller, so that's probably, maybe more to the 100 kilo estimate, because it is smaller.
Okay.
But that I would say that's sort of a rough range that we give. But these things are very difficult to estimate. What we see in the seismic network, where we calculate something which would be a magnitude if it had been an earthquake, to convert that to an amount of explosives is something that people have been working on for many, many years, and it goes all the way back to the nuclear tests in the 50s.
Okay.
So there are equations to equate, magnitude 5, I think magnitude 5.8, that was the Hiroshima nuclear explosion. And so there are equations to do this, but they're different in different areas, in different circumstances. And there are underwater explosion conversions, which our colleagues in Norway used, and they come up with estimates of 600 to 900 kilos for the second blast, because they're using these equations. But we are comparing to these blasts that occur in the same area, which are recorded on our instruments in our geological setting.
You're doing it because you have this data that the Navy has been giving you over the years, and so
Yes.
you're able to make that sort of informed calculation.
Right. Yeah, that's correct.
Now, let me ask you a question. Your German colleagues that I've spoken to are hesitant to call it a blast. Why is that?
I don't know. Okay. I would have to speak. I haven't talked to them. I don't think we have any doubts, really. These are blasts. I have looked, we have collected data from Germany to look at as well, because obviously from Sweden you get data basically only on one side, but we also have Danish data from the island of Bornholm, which is extremely useful in this case. We also have the German data, but that turns out their stations are very noisy, so it's very difficult to see clear seismic signals on the German stations. So we actually just a few hours ago here decided that we probably not use that data because it's so noisy.
So the data you were using,
and necessarily saying that the Germans are probably interpreting their own data in a good way, but that doesn't really help us.
The data you're using, is it from that station on the Danish island?
We're using that data and the data from all the Swedish stations, or not all of them, but the Swedish stations within about 250 kilometers or so, which is sort of optimal for location purposes. The second blast, which was a little bit larger, is actually visible on our seismic stations across the entire country. You can see them 1,800 kilometers away on the northernmost station.
And is that common for blasts that you've picked up in the past?
It's not uncommon. It's a very good coupling. If you blast in the water, you get very good coupling to rock as well. So we see that frequently in blasting, that they are, you can trace these blasts on the seismic stations in much of the country if they are in this size. Yes.
That's really interesting. Let me pull up this email exchange that I've had with your German colleagues, because I want to make sure I understand correctly what they've explained to me. So they called it two distinct events, two spikes, one followed by stronger seismic noise than before the spikes. They're just describing that there's a change in noise levels. Can you explain to me what that means, a change in noise levels?
What we're measuring at the seismic stations is how the ground vibrates, basically. So that's what the instruments pick up. And there's always a basic vibration of different kinds of seismic sort of noise waves. So the station is always vibrating a little bit. The biggest source of vibration is actually the big waves hitting the continental slopes, and big currents in the deep oceans creates seismic noise. And that's ever present everywhere on Earth. Wherever you measure, you see this noise. And then depending on where you are, depending on the type of rock that you have, the noise can be larger or smaller. We want to put our stations as far away as we can from what we call cultural noise. So from houses and roads and machinery, especially rotating machinery, is very annoying because it creates noise of a certain frequency. So we have our seismic stations often a couple of 100 meters out into the forest, and then we have electricity and data cables going out from a house or a garage or a summer house or something. So it's very important to have these stable, low noise conditions. And what the Germans are describing here, something we also saw in our data, that this sort of vibration of the ground before the event happened was at a certain level. Let's say we had this much vibrations, and then the event happens and you have all sorts of waves coming from the blast, and it takes a while, a couple of minutes, a bit more, before these waves sort of go down and go back to the background noise level.
Okay.
But here it turns out that when you get a few minutes down the line, it doesn't go back to the same noise level we had prior to the blast. The noise level is actually significantly higher. And this is very interesting. This means that there's something there creating this noise continuously. And one possible explanation that we have been discussing, I'm not saying that this is the correct thing, but perhaps this is what we're seeing now, is the bubbles coming out of the pipeline. So we see the gas streaming out, creating these big bubbles that we've seen in the videos. And it's possible, at least, that this increase in noise level is the gas flowing out of the pipeline that we're seeing. Or if it creates some sort of noise in the damaged pipeline as the gas goes out. Because we only see this as closer stations, not at stations further away from the event.
Okay, this is really, really clear and very interesting, and I've learned a lot, and I'm sure people who will watch this video will too. I think this is a lot more information than most of us have been getting. Is there anything else that, in your mind is left unanswered from a scientific point of view? I mean, we've touched upon a few of them, but is there anything else that you're working on, that you're looking into?
So we're comparing the blast data that we have from the Navy to Monday's data to see if we can see any sort of obvious differences that could point to, because what we have in the Navy is, of course, a mine or an explosive device with 100 kilos or 150 kilos that goes boom. But you could imagine that on the pipeline there are other effects of rupturing, or if there's something, if the pipeline breaks, the gas flows out, and there's some other mechanism in what we're seeing. So that's something that we've been trying to look at. It doesn't look like that. It looks very much like a single blast, but we are looking into it. We're also looking into this fact, as we touched upon earlier, there are 2 leaks in the northern part, but we only see one blast. That blast looks a little bit different than the first blast. So we're trying to estimate, could it be that there's been 2 blasts, but they're so close in time that the waves actually interfere as we are measuring them? So that's also something we're looking at now. Could that be the case? It's not trivial to disentangle that, but that's something we're also looking at the moment.
So let me make sure I understand your first point correctly. You're saying that you're looking at whether or not the visual graphs that you have, the data that you have, whether or not it's showcasing, for example, like a slow build of perhaps a rupture versus one single blast. Is that
yes.
correct? Okay.
Yes. Yeah, they're right. Basically seeing, do we see anything that does not look like a single blast? Is there any evidence of something else going on?
Okay.
That's what we're trying to look at.
I hope that you'll keep me updated on your discoveries. And do you think there's anything else the public should be aware of as we're trying to find out more about this?
There's probably nothing I can think of right now. At least I think we covered a lot of it.